As opposed to quantizing one sample, one may take more than one sample, hundreds of samples, 2 samples, and so on, and then quantize a number of samples together. These will allow us to more efficiently quantize our signals or waveforms or images more efficiently with less number of bits and less quantization error. In this video, we learn the concepts of quantizing multiple samples at once. These concepts are linked to machine learning or lots of other applications as well. So basically, instead of taking one sample by one sample quantization, we take, let's say, n samples, n inputs together, and we form a vector. So we'll have vector x, which is the first component, the second component, n component. So we'll have n tuple, and then depending where this vector is in the n-dimensional space, we quantize it. So instead of partitioning the real line, we partition the space of n-dimensional into k regions. If we want to allocate a number of bits, we could divide it into subregions. And if x is in the first region, we quantize it to first value. If x is in the second region, we quantize it second value, and so on. So to quantize value in each region is one fixed value. So at a transmitter, the job of transmitter is to verify in which region x is, and then you will only transmit the index of that region. So you will tell, oh, this is in region 5 or 6 and so on, and the receiver will know where is your signal. So if the number of regions is large enough, then the regions are small enough, and you roughly at the receiver know what was your signal. So you will construct the center of the region. So for n sample, if we allocate k region, so the number of bits for n sample is log 2 of k. And because I have n samples, if I divide these, so r is the number of bits allocated per sample. By increasing the dimension of space, n, we could make these quantization more efficiently. So we'll look at this, how this works. Similarly to what we have proven for scalar quantization, the quantized value for each region is the average of your input over that region, which is the integral of x fx of x dx over that region divided by this normalized value. So the center of each region is just the average of data in that region. The vector quantization is nothing more than mapping an n-dimensional vector, which is in space, into a finite set of vectors. So is x hat 1, etc. up to x hat n. Each vector is called a code word, for instance x2 or x1. So each of these centers, so the transmitter will transmit the label of these code words, and the receiver knows which one is to be taken. So x1, x2, xn are code words. So we have n code words, and the number of bits here for these is log 2 of capital N. And the set of all code words is called a code book. Sometimes some people, they refer to it as a dictionary. So each code word is associated with a region. So all those points in your n-dimensional space, which are closest to your center point, are assigned to xi. So at the transmitter, your input is x. You calculate the distance with xi's, and then you will verify to which one you are the closest one, and then you take the index of that point. So this is how your signal is quantized. And then this index at the receiver will reproduce x hat I. So you are encoded to the closest point to you. So this Ri is called the Voronoi region. So let's see how this works. Suppose that I have x hat high here, x hat 2 here, and I say this is third one, fourth one, and so on. So these points, I calculate the distance between this one and x1. I calculate this input with x2, with x3, etc. And then when I see that the closest point to this one here. So this signal is encoded with 1. But this one is closest to this, so this is encoded in 2, because this is in region 2. So this area, the gray area, is region 1. All these points in the gray area are encoded with region 1. And all these points in this region are encoded with capital N, because they are closer to this center point. And for example, these points, all these points are encoded with this one. So if I want to verify, let's say between x2 and x1, the set of points which are closer to x1, if I want to plot it, I have to draw the line between x1 and x2, consider the midpoint, draw a perpendicular line, and any point on the right side belongs to R1, any point to the left side belongs to R2. Similarly, if you want to verify which points are closer to this point versus this one, so you draw a line, get the midpoint, draw a perpendicular line, and then all points, this side belongs to R1 and this side do not belong to R1. And similarly, you can, for this one, you can draw a line perpendicular to that. This side is R1 and this side is not R1. Similarly, you calculate this one, draw a perpendicular line, and then you get this one. So the intersection of all points which are closer to x1 forms region L. So this is called a Voronoi region associated with this point, and so on. So the vector quantization is fully characterized by these x1, x2, etc., because the regions are determined and any input belongs to only one of them. So the encoding and decoding are clear. This is another example. The second question is that if I have the center points x hat 1, x hat 2, etc., I have the regions, I could do quantization and I could do dequantization. But if you want to design the set of these points, which points you should get in order to have less bits, what you could do is first you could randomly select some center points and then design your regions and then determine which set of points are in this region. For instance, these points that are in here, and then average them. So all these data that are here, let's say x1, x2, x3, etc., and then you say summation of, let's say, all those xi's which are in this region divided by the total number of them, then you will get a new center point, which is not exactly this red point, but is a little bit displaced. And then you do this for all the points, and then you will find a new set of center points. Then you repeat these several times. This is called k-means clustering. So this is the main tools for unsupervised learning and machine learning. So it's very close to. So this is x hat 1. So and then x hat 2 determines region 2, etc. And then you could evolve.